Welcome. In this video we'll discuss generating a project input database for the GCBM. To do this, the Recliner to GCBM tool will be used. This is the only non-Python data preparation tool that will be used. The Recliner to GCBM tool is written in C# and it bridges the gap between the aspatial CBM CFS3 and the spatially explicit GCBM. It uses the same default archive index database with Canadian non-spatial parameters as the CBM CFS3. It can import a yield table in CSV or Microsoft Excel format, and after a bit of configuration it will generate the SQLite formatted GCBM input database. Users can find the output in the input_database folder, and a recliner to GCBM.log file will also be generated. This is the only log file that will be generated in the Tools folder as opposed to the Logs folder. As previously discussed, the GCBM uses an archive index database and needs a yield table, and the yield curves for this example dataset are stored in the yield.csv file. Displayed here is a portion of the yield.csv file, and as can be seen, each record has two classifiers, with each classifier set being linked to a species or forest type in the archive index database, and these are followed by gross merchantable volume values in meters cubed per hectare from age 0 in 10-year age increments. Before configuring the input database, the classifier layer names in the tiler script that was set up should be noted. The names are always under the user's control, and they just need to be consistent between the tiler and the Recliner to GCBM tool. To start up the tool, users must go to the input_database folder in the one_standalone_template folder and double-click on the run_recliner to GCBM_GUI.bat file to launch it. Once the configuration project window opens, the first step is to browse to the archive index database file called archive_beta_install.mdb, also located in the input_database folder in the one_standalone_template folder. Next, users must specify the output database. This is the database that will be generated at the end of the process. Again, users must browse to the input_database folder, select the GCBM_input.db file, click on the Save button, and click on the Yes button to allow replacement of the file. To proceed to the next window, users will simply click on the Next button. In this window, users can begin adding their classifier layers. They can start by clicking on the Add button twice. An Add Classifier window will appear where users will need to set up a few components. The first is to enter a classifier name in the classifier name box. Names entered will need to be the same as those previously entered in the tiler script. If we return to the tiler script and review the classifier layers on lines 57 and 58, the classifier names classifier 1 and classifier 2 can be copied directly from the script and pasted into the Add Classifier window. If entered manually, note that classifier names are case sensitive. We'll proceed to enter classifier 1 in the classifier name box. The next step is to browse to and open the yield table file, yield.csv, located in the input_database folder in the one_standalone_template folder. Once selected and opened, the table in the Add Classifier window will be automatically populated with the yield.csv file contents. Next, the column of data associated with classifier 1 will need to be identified. To do this, click on the Select button and click anywhere in column A. The last step is to specify whether or not the input data includes a header row using the header row checkbox. A checkmark indicates that it does, and it will be checked by default. In this case, the data does contain a header row, so it can be left as is, and the OK button can be clicked. All of these steps must then be repeated for classifier 2, including the selection of the yield.csv file, clicking on the Select button, and clicking anywhere in column B, in this instance, ensuring that the header row checkbox is checked, and finally clicking on the OK button. With the information entered for both project classifiers, the Next button can be clicked. In the next step, the growth in yield or volume over age curves that describe stand growth will need to be set up. This information is linked to the spatial inventory using the two classifiers that have been identified. In the Configure Growth Curves window, the first step is to identify the file containing the yield curve data. Users must click on the Browse button, go to the input_database folder, and open the yield.csv file again. As a result, the table in the Configure Growth Curves window will populate with the data for the two classifiers. Again, since the data in the CSV file has a header row, users should ensure that the header row checkbox is checked. Next, the classifiers will need to be mapped. The reason this mapping is required again is because classifier values could potentially come from different files. In this example, they're all coming from the yield.csv file. To map classifier 1, click on the Select button next to the classifier 1 in the window, and then click anywhere in column A in the table. Then, repeat the steps for classifier 2 and map it to column B. The value in the growth curve interval box represents the number of years between volume increments for all growth curves in the yield.csv file. In this example dataset, the interval is 10 years. The header row column labels in the table acknowledges this as each label value increases by 10. As such, 10 must be entered in the growth curve interval box. Next, users must identify the column representing the leading species or forest type, or the Archive Index Database Tree Species column labeled AIDB SPP. By GCBM format convention, this column must be in between the classifier columns and the first volume increment column. In this example, it's column C. Users must click on the Select button for species and then click anywhere in column C. Lastly, users need to identify which columns represent the beginning and end of the volume increments in the increment boxes. To proceed, click on the first ... associated with increment. Since the volume increments begin in column D, users must click anywhere in that column. Next, users must click on the second ... button, then scroll to the last field of values, column AM, and click anywhere in that column. Users can then proceed to click on the next button. Transition rules basically describe what happens after a specific stand type is disturbed by a specific disturbance type. These rules are linked and created by the tiler script. In the example dataset, few transition rules were specified. In fact, only one transition rule was specified. In the tiler script, it's on lines 88 to 91. Setting up transition rules is optional for disturbance events, and the one included in this project simply resets the stand age to 0 after any disturbance event. Just as was done with the yield curves, users will need to inform the tool about their transition rules file. In the Configure Transition Rules window, users must click on the Browse button to identify and open their transition rules file, which in this example is located in the one_standalone_template layers and tiled folders and is called transition_rules.csv. Once selected and opened in the Configure Transition Rules window, ensure that the header row checkbox is checked. There are many options in this window, some of which are advanced or optional. For basic transition rules, the classifiers must also be mapped. In the Transition Classifiers box, the Select button for Classifier 1 is clicked, and any cell in column D is clicked, and then the Select button for Classifier 2 is clicked, and any cell in column E is clicked. Next, the column representing ID values must be mapped. ID values can be strings, but in this example they are numerical values. To map the column, the ... button for the name box is clicked, and then any cell in column A is clicked. The mapping of the two remaining basic components follows similar steps. Regen delay should be mapped to column B, and reset age should be mapped to column C. Once the basic mapping is completed, the next button is clicked. Making changes on the Configure Disturbance Category screen is optional. It's one of the more advanced GCBM module components, so it will not be discussed at this point, and the next button will be clicked. The input database has now been set up, and users always have the option to go back and make changes, if necessary. One thing that users might want to do in the Create Project window is save the configuration, in case something goes wrong. Doing this will also allow users to regenerate the input database from the command line. When users click on and execute the run_all.bat file, it takes a previously saved configuration and regenerates the input database. This allows users to go back and modify values. For example, adding extra yield curves to the yield table and then regenerating the database without having to redo all of the configuration steps again. In this example, the existing configuration will be overridden by clicking on the Load button. If everything goes well and everything was set up correctly, users will see the progress bar display without errors. To complete the process, the last step would be to click on the Done button. This completes the steps to generate a GCBM input database. In the next video, we'll cover the steps to configure and run a GCBM project.